right, with respect to the x-axis.
Right.
And then we have a y-polarized beam instant on the quarter wave plate, right? So just looking at it, we have that this much of it is in the slow axis direction, and this much of it is in the fast axis direction. And so you know, you do this, and then it propagates through. This is going to lead it, right?
Yeah.
And so that means we're going to have rotation counterclockwise. So we're going to get a state that looks like this, right?
Right.
Elliptical.
That's what we intuitively expect.
Yeah.
But the resulting Jones matrix doesn't really show that. Or I guess you can't really tell from the
Yeah, you can't really tell.
You
But
just
that is
assume.
what it is.
Okay. Is it
Yeah.
safe to assume that, hey, it's going to be an elliptical?
Well, it's not even assumption. You absolutely know it's elliptical.
Okay.
There's no assumption necessary. It's elliptical.
Okay.
So, and anytime you have a result where you have a Jones vector of this form, and that is not 0 or pi, you know you have elliptical. So anything that you can, anything that's more complicated, some complex thing here, some complex thing here, as long as the phase angles of the complex numbers are not the same, or 180 degrees out of phase, then it's going to be elliptical.
Okay.
Yeah. Okay.
Can I ask a question?
Sure.
For question number 5, part B,
Okay, and which one is that?
is the polarizer in the extraction?
Yeah. Polarizer.
Part B, I have question.
I think by part B, where they rotate the polarizer by angle beta.
Yeah.
Yeah, and you want to
Yeah.
check that polarizer B squared is equal to polarizer B.
Yeah.
Yeah, my question is that we shouldn't consider Jones matrix of wave plate for that. I mean, just we should multiply R minus beta and R beta.
So you have a Jones matrix, and it's R minus beta 1, 0, 0, 0, R of beta,
All right.
and it is whatever it is.
But for part B, we don't know that is the ideal polarizer. Right?
Yeah, it is. Nothing's changed compared to A, so it's still ideal.
Okay.
Yeah. Yeah, and then basically
Yeah, then I know.
Yeah.
that.
That is easy.
Yeah, right.
Yeah.
It's just going to be that. Yeah. Okay. Okay, any other questions?
I actually have one.
Yep.
This is, it kind of deals with what we were doing in 2, but it also shows up in number 3, part B, where you go from, I guess, a Jones matrix and you're trying to put it into a complex or representational form.
Okay.
And at least in wrestling with it, I haven't been able to figure out how to do that.
Which one is it? 3B?
Yeah, it's 3B, which I think it relies on 3A, which...
3, so
Yeah.
3 is the Babinet-Soleil compensator?
No.
I don't remember.
The weight is like right here.
Oh. So I gave you a different homework?
Yeah.
Okay. All right. Oh, and I had that one wrong. It was polarization in the y-axis instead of the x, right? It's the same principle.
Yeah.
Okay. Okay, so slow axis is at an angle beta, right? And then we've got instant light that's X polarized. And then the question is what?
B is to put in complex, is that what B said?
Yeah,
Yeah.
and so in A, you get something,
Complex.
and let me just write it this way for the moment, even though it doesn't work out that nicely. But you know that if you pull an AX out, you get AY over AX e to the J delta, and that is the complex number representation. So whatever you get in A, if you pull the X component out, which means you're going to divide this by the X component, it will be the complex number representation. So that's it.
So do you just need one complex number and that represents the entire polarization state?
Yeah, so in other words, every point in the complex plane represents a unique polarization state. And when you go off to infinity in any direction, that's always gets you to vertical linear polarization. So does that answer the question?
I may just need to come talk to you afterwards about it.
Well, I mean, so you're going to have something that's uglier.
Yeah, I'm looking
So
at the
some-
ugly right
Some
now.
X component, some Y component.
Yeah.
If you pull the X component out, you're going to have this, right?
Yeah.
And that is the complex number representation.
Okay. Yeah, I was wondering how you got the complex component out of the top part of the X component. Okay, that makes sense.
Yeah.
Cool. All right.
Okay.
It's easy. All right.
Yeah, so it's not bad.
No, not at all.
Okay.
Cool.
Let's see, Jace, would you mind shutting the door over there? Thanks. Okay, any other questions before we get going?
No way you have something new to teach.
What's that?
Said there's no way you have something new to teach.
No way, we're just gonna rehash the same old, right? Oh, not even close.
Everything about life.
We're getting there, we're making a dent. Okay, so last time we talked about form birefringence, right? Margaret polarizers. We looked at some examples from work that we'd done some time ago. We talked about how to generate any arbitrary polarization state with a quarter wave plate and a polarizer. And if you can generate any arbitrary state with a quarter wave plate and a polarizer, you can determine any state with a quarter wave plate and a polarizer. Okay, so what we want to do now is take a little bit of a different look at things. And let's get there by refreshing our memories. What assumptions did we make when we started talking about polarization?
Propagation Z direction.
Monochromatic. And then what, Mom?
Propagation Z direction.
Z direction. Okay, anything else?
So,
Uniaxial materials, right?
Yeah. For the wave plates, Right. Okay, well, so plane wave, which is a particular type of monochromatic, and we assume that the wave vector is in the Z direction with no loss of generality.
assumed it was fully polarized?
Pardon?
We were assuming it was fully polarized?
Fully polarized. It turns out that because we assumed it was monochromatic, then we represented the electric field, right? And because we wrote down the electric field for a monochromatic beam, it is fully polarized. There's nothing about it that's not polarized.
So in order to have partial polarizations, you have to have a non-monochromatic, a polychromatic source.
Yes. Yeah. Yeah, Jason?
What does the partial polarization, what is that?
That's exactly what we want to get to today.
Okay.
Yeah. We want to see what that is. So, we've been doing a lot with Jones vectors. And the Jones vector, we are representing the electric field of a monochromatic plane wave. So by definition, we're representing a fully polarized beam. So the question is, how do we deal with partially polarized or unpolarized beams, and what does that even mean? So that's what we want to get to. And it turns out that there is a different way of representing polarization state called a Stokes vector. So instead of a Jones vector, now we're going to start talking about Stokes vectors. And let's assume, for the moment, that we're still talking about the monochromatic case. And let's also assume that we have a plane wave and that the direction of propagation is in the z direction. Then we can write down the real electric field components, which are going to be an x component and a y component. And we can write them as simply E naught x, some constant real number, cosine omega t minus kz plus delta x, E naught y, constant real number, cosine omega t minus kz plus delta y, and delta is just delta y minus delta x as usual. Okay, so simple enough to write down the expressions for the electric field components, the real electric field components. And what we're going to do is define a Stokes vector that has four components. So S0, S1, S2, and S3. And we'll write them in terms of, by the way, what physical thing does that represent?
Amplitude.
Amplitude of? In the x, the x component of the electric field, amplitude. Likewise for the y component. And then the only other thing we really care about is delta, the phase difference between the y and the x components. So those three things define a polarization state. So it turns out that S0 then is x squared, actually it's the amplitude, E0 x squared plus E0 y squared, and S1 is equal to E0 x squared minus E0 y squared, and S2 is equal to 2 E naught x, E naught y times cosine of delta, and S3 is 2 E naught x, E naught y, sine of delta. And then, so this represents some arbitrary elliptical polarization state with an orientation angle phi. And if this is the semi-major axis A, semi-minor axis B, and we draw a little rectangular box enclosing it, then we have this triangle A, B, and the hypotenuse. So this angle here is the ellipticity angle, theta. And if we go back to our definitions before, tangent of 2 times the orientation angle, and just look at what we've got up here, it turns out that that is S2 over S1. And the sine of 2 times the Latisti angle is S3 over S0. So if you go back to our definitions before, or at least our expressions before, for tangent of 2 phi, sine of 2 theta, which are phrased in terms of E naught x, E naught y, and delta, you'll find that it's exactly these ratios given the Stokes vector components. Okay, I think that's interesting.
You said that we use Stokes vectors when we don't have a light that is fully polarized, right?
It's good for that case. In other words, you cannot use Jones vectors if the light is not fully polarized. You have to do something else. Generally, the something else is Stokes vector.
But you can represent
Fully polarized with the Stokes vector, yes.
Which is what we're
absolutely.
doing right now.
Yes, which is what we're doing right now because we're considering the monochromatic case. And so, one can show then that S0 squared is S1 squared plus S2 squared plus S3 squared. So if you just take these things, square and sum them, you will get S0 squared. And that is the hallmark of fully polarized light, when that is true.
So if that is true, it is always fully polarized.
And now what we want to do is take a look at what happens with Stokes vectors when we have partially polarized light. And what that means. What is partially polarized light?
Just really quick, that bottom, it's sine 2 theta equals S3 over S naught, S0.
Yes, correct. Okay. So, in general, S0 squared is greater than or at most equal to S1 squared plus S2 squared plus S3 squared. And the equal sign is only true if we have fully polarized light. So, first question is, what even does it mean to have partially polarized light?
So that would probably mean that one of the colors is polarized and the other, another color in the beam would not be.
Possibly. Another way to look at it is, do you remember when we talked about incoherent light? And we plotted the electric field as a function of time. We did it in a scalar model. So we have this scalar field as a function of time. Actually, we plotted the real version of it. And for incoherent light, what did it look like?
Is the electric field?
Yeah,
Scalar.
the optical field, scalar optical field. For incoherent light, what did the scalar field look like as a function of time? No? So if it was fully coherent, what would it look like as a function of time? The scalar field. The real scalar field.
Cosine sinusoidal.
Yeah, it'd be sinusoidal. So that would be a coherent beam. In other words, it's completely monochromatic. The coherence time goes as 1 over the spectral width. Spectral width is 0. Coherence time is infinite. Okay, so what does it look like for a incoherent beam? What is the...
Something not like.
Yeah, it's just not periodic. So it's is varying. At every point in time, there's a well-defined field, and you could measure it if you could measure things on that time scale. Generally, you can't, but if you could, there'd be a well-defined field. It's just that the field from point to point in time, at least for reasonable separations of time, is just not correlated. So given the field at one point in time, you can't predict what it is sometime later, because it's uncorrelated. Yeah.
So to go to the partially polarized light, do we have to drop the monochromatic assumption?
Yeah. So for partially polarized light, if we were to freeze time, this is one way to think about it. If we were to freeze time t equals 0, then it has a well-defined polarization state. Some orientation angle phi, some ellipticity angle theta. But if we look a little time later, say at t1, now it has some completely different polarization state with orientation angle phi and ellipticity angle theta. It's completely different. And having knowledge of the polarization state at time t equals 0 doesn't give us anything in terms of knowing what it is at time t equals 1. Et cetera, as you continue on in time. So in other words, the polarization state is random as a function of time. It's rapidly switching from one state to another state. All kinds of arbitrary states in no fixed pattern. So that would be an instantaneous picture of what unpolarized light is. Does that make sense? Okay. So partially polarized light would be something in between. That if you go from time t equals 0 to t equals 1, there is some correlation between the polarization states. But it's not completely correlated. So that would be partially polarized light. Okay, so in the case of unpolarized or partially polarized light, then what we do is, in other words, for this part, we use a complex representation for the field. So in other words, the x component as a function of time, we can write it as some magnitude times e to the j omega t, but that magnitude is itself time dependent. So we could say that it's E0x of t e to the j delta x of t. And likewise, the complex y component we can write like this, and this amplitude is time dependent. Okay, so if we write it that way, then what we can do is these Stokes vector components, we would write them like this. We would say that S0 is the magnitude squared of the complex electric field in the x direction plus the magnitude squared of the complex field in the y direction. S1 would be magnitude squared in the x direction minus magnitude squared in the y direction. And S2 would be EX complex conjugate times EY, or actually EX EY complex conjugate, minus EX complex conjugate EY. And then S3 would be J times EX complex conjugate, or EXEY complex conjugate minus EX complex conjugate EY. And these things, in other words, are all time average quantities. And I'm not going to drag us through the math as to how that is, but they are all time average quantities. So, some things to note. For the Stokes vector component S0, notice that it is proportional to the irradiance of the beam. Right? Because this, we take this and divide by 1 over 2 times eta, it is the irradiance of the beam. Okay, great. So, we can define the degree of polarization in the following way. P, degree of polarization, is the irradiance of the polarized fraction of the light divided by the irradiance of the entire amount of light. And that is equal to the square root S1 squared plus S2 squared plus S3 squared over S0. And so you'll notice the degree of polarization P is bounded by 0 and 1. So if P is 1, we have fully polarized light. If P is 0, we have completely unpolarized light. Yeah.
What's the difference between I-pole and I-naught?
So I-pole is the irradiance of the polarized fraction of the light. So if we had some way of taking a beam and just removing the unpolarized part, we'd be left with only the polarized part.
Okay,
And that would be the irradiance
And
of
then
the
I-naught is
polarized
the radius of the whole thing.
of the whole thing.
Okay.
Yeah.
What are the ranges for P again? Or what do they represent, the 0 and 1?
So 1 is fully polarized. 0 is completely unpolarized. Okay, so we'll get back to this. But before we do, let's look at some Stokes vectors for some fully polarized states, polarization states. So in other words, how would we represent linear polarization in x hat? Well, the Stokes vector would be 1, 1, 0, 0 in that case. And linear polarization in y hat, the Stokes vector would be 1, minus 1, 0, 0. And you can go back to the monochromatic case for fully polarized Stokes vectors and see how that works out. And see that, you know, this is 1, this is 1, this is 0, this is 0 when you have linear polarization in x, etc. And then linear polarization at 45 degrees to x hat, and that's equal to S 1, 0, 1, 0. And if we have linear polarization at minus 45 degrees to x hat, then that's 1, 0, minus 1, 0. And then finally, if we have clockwise circular polarization, that's S equal to 1, 0, 0, 1. And counterclockwise, circular polarization, 1, 0, 0, minus 1. Okay, so, fine. Actually, there's one point. Yeah, that's good. Okay. So now, let's talk about how you actually measure the Stokes vector. Because one thing that's nice about the Stokes vector representation is it is really easy to measure a Stokes vector given any beam in the lab. And so let's assume that we have the following setup. Let's say that we have some retarder, and that wave plate, we have the slow axis in the x direction, fast axis in the y direction, and it has some retardance gamma. We'll leave it unspecified for the moment. And then we'll follow the retarder with a linear polarizer at angle beta. And then one can show, I'm not going to show it, but one can show that the irradiance through here, so we've got light going through here, and we're worrying about what's the irradiance we measure on the detector, that the irradiance is, of course, going to be a function of beta, the angle of the polarizer, and gamma, how much retardance we have on the wave plate. And if you do the math, it works out to be 1/2 quantity S0 plus S1 cosine of 2 times beta plus S2 times cosine of gamma sine of 2 beta plus S3 cosine of gamma, no, sine of gamma, sine of 2 beta. So that's the irradiance that we'll measure in terms of beta and gamma for those settings.
Is this a
And
partially polarized case?
all cases. Yeah, fully, partially, or completely unpolarized. That's what we'll measure. And, you know, if you want some fun one evening, derive that. So we can specify a measurement, I, by what we set beta at. Let's say we set it at 0 degrees. And what we set gamma to. Let's say we set gamma to 0 degrees. What measurement is that? I mean, what am I using to make that measurement? Pardon?
Like nothing's there.
There's one thing there.
No, that's not, that's not.
So the retardance is 0, so yeah,
It's
there's no wave plate.
And S1.
But beta 0,
Oh, so it's strictly X kind of linear polarized.
yeah, so it's just a linear polarizer in X, right? So this is just a linear polarizer oriented in the X direction. And then if I made a measurement with beta at 45 degrees, retardance of 0, what's that situation?
Linear polarizer at an angle of 45 degrees.
Yeah, linear polarizer at 45 degrees to X. And then if I make a measurement 90 degrees, 0, that's linear polarizer in direction. And it turns out that if I measure with only those three cases, I can get S0, S1, and S2. So with a single polarizer, rotating it to three different angles, I can measure the first three Stokes components.
Does each one give you like S1, S2, S3, or is it like?
No, it's a combination. It's a combination. Yeah, we'll write it down shortly. So from these, we can get S0, S1, and S2. And then if I do one more measurement, I can get S4, or rather S3. That one more measurement is I at 45 degrees, 90 degrees. So what is that? What's the measurement made with? So the 45 degrees means?
45 degree polarizer.
Yeah, linear polarizer at 45 degrees. The 90 degree means? Quarter wave plate. So if I have this and those, then I can get S0, S1, S2, and S3. And let's write down how that is. But the interesting thing is with just a single polarizer, you can get 3 out of the 4 Stokes vector components.
Seems just algebraically get the fourth one then.
Now you have to have that measurement with the quarter wave plate. Yeah, Jason?
Wouldn't it be easier to make theta equal to 90 as well? And you get rid of that S1 term? Maybe your equation
Here?
would just be easier to solve? Yeah, in this last measurement you make. Or would that mess something up?
It would mess something up because then beta is oriented along the fast axis, so you pretty much get no information from the quarter wave plate.
Oh, okay.
Yeah. Okay. So, with those measurements then, I can then go back and solve for what S0 through S3 are. I've got 4 measurements, 4 unknowns. If I do the algebra, then what I find is that S0 is equal to I, 0 degrees, 0 degrees, plus I, 90 degrees, 0 degrees. So what are those two things again? Yeah, and so that is a pretty much intuitively obvious statement, right? So, okay, fine. S1 then is the linear combination of I 0 degrees, 0 degrees minus I 90 degrees, 0 degrees. So, also simple to measure. And then S2, that's I 45 degrees, 0 degrees, minus I 0 degrees, 0 degrees, minus I 90 degrees, 0 degrees. And then S4 is, oh, I forgot, there's a 2 right here. 2 in front of that. Yeah, so this is then 2I 45 degrees, 90 degrees. That's where we use our quarter wave plate measurement.
So is that 2 multiplied to the whole thing?
Yeah, 2 multiplying that minus I of 0 degrees, 0 degrees, minus I of 90 degrees, 0 degrees.
50 minus 3.
Oh, yes, thank you very much. Perfect. Thanks. Okay. So with these 4 measurements then, I can get 4 Stokes parameters. Okay. Just for fun, let's do the following. I want to flip on that projector.
too many buttons there.
I'm not sure this might be this one.
Oh.
This jack here's sagging pretty bad on its own weight.
Oh. All right, looking auspicious. All right, Wes, just stand right there. Okay, so remember I showed you this paper, was it last time?
Is this the one where you made all the little like micro polarizers?
Yeah. So let's just take a closer look at this. This is a unit cell replicated across the full focal plane array. So what is this?
That's the 0, 0, or
It's a wire grid polarizer, right? What does it pass? Which polarization state?
Y polarization.
Y. What is that?
Passes X polarization.
Passes X. Passes,
45 degrees.
yeah, minus 45, well, whatever. And what's that? It's 45 degrees on top of a formed birefringent quarter wave plate.
I didn't quite understand why the top left one passes. It's linear. It's a polarizer along y-axis.
Because electric field oscillating this direction can excite a surface current. Excites a surface current that reflects the light. This direction, because the spacing is so much smaller in the wavelength, there's no surface current, so light just goes right on through. Okay, so we make basically 4 measurements with those 4 things. Do those measurements look familiar now? Yeah?
Mm.
So this is a way of taking a focal plane array that's sensitive to how much light falls on each pixel, and now make polarization measurements. Take groups of 4 pixels, group them together, make a single polarization measurement with those 4 pixels. So now you're measuring polarization state across your focal plane array instead of measuring light intensity. Therefore, you can take a scene, and rather than measure how much light's coming at you from each point in the scene, you can measure the polarization state coming from each point in the scene. So that's called imaging polarimetry. You're imaging polarization state.
So then what's the difference between what we're doing here and what we did last time where we had just the polarizer and the quarter wave plate and we could determine what the polarization was?
So on that, we have to be able to rotate the two relative to each other. So here, we're doing just a fixed set of measurements, maybe 4, and figuring out what the polarization state is based upon those 4 fixed measurements. Okay, so basically what we're doing here is fabricating these polarization filters and sticking them on top of a infrared focal plane array and turning it into an imaging polarimetry system. So, and it all goes back to Stokes vectors. And so we could measure the full Stokes vector point by point throughout a scene. Okay, thank you, Wes.
How is it going to work with electro anyway?
Yeah, unless we were at the beginning of looking at it, then it wouldn't.
Yes, then it would work.
Okay, great.
How all this we just learned still take into account the partial aspect of what we're kind of learning?
Oh, because we measure these things,
Yeah.
and then we can easily calculate the degree of polarization. And it's going to be something between 0 and 1. If it's 1, it's fully polarized. If it's 0, it's completely unpolarized.
Now, with using something like that in say an ecosystem, where you're sending out a laser pulse of some sort coming back, would we expect it to be much closer to 1?
Totally depends on the scene you're illuminating. So man-made objects tend to reflect and tend to emit light that has some degree of polarization. Natural objects tend to be closer to no polarization. And that's what makes imaging polarimetry really useful for some applications, is it's easy to tell man-made objects from natural objects.
Well, why is that? You know,
Oh, because man-made objects, I mean, what do we make stuff out of? Metal, plastic, glass,
Refined.
tend to have very smooth surfaces. And natural objects, what are they made out of?
Everything mixed together.
Organic materials, rocks, whatever. It's very rare to get a smooth surface. So you tend to have a lot of scattering. Scattering is a polarization-dependent process. So you tend to be left with more unpolarized light from natural objects.
So you had said that partially polarized light means that there is some correlation, right? That you will be able to tell.
Yeah, so it depends on how far out in time do you go.
Okay.
Do you go out 3 femtoseconds and it's still polarized? Okay, partially polarized. Do you go out 3 nanoseconds and now it's not polarized anymore? Then you're in the partial polarization case. If you go out 3 nanoseconds and you're still polarized, you're pretty polarized.
Okay, and that was my question, and what it meant to be a quarter, what P being a quarter to P being 3/4.
Yeah. Yeah, it's just
The amount of time that it stays.
yeah, exactly. Right. Okay. So now, what we want to do is circle back. And remember, we talked about all these different ways of representing polarization states. And one of those ways was the Poincare sphere. So let's see what Stokes vectors have to do with Poincare sphere. So if you go back to our definitions of the components of the Stokes vector, it turns out that, again, one can show, and I'm not going to do all the showing, one can show that you can also write the Stokes vectors in the following way. S1 is S0 times cosine of 2 times theta. What's theta? Elasticity angle. Times cosine of 2 times phi. Phi is the orientation angle. And S2 is S0 cosine 2 times theta sine 2 times the orientation angle. And S3 is S0 sine of 2 times theta. So one can show. And notice that we could just normalize these by S0. So if I said, let's say S1 prime is S1 over S0, then that's cosine 2 theta, cosine 2 phi. Put a little separator there. S2 prime, S2 over S0. So we have cosine 2 theta, sine 2 phi. And S3 prime is S3 over S0, which is just sine of 2 theta. Now, does that ring a bell?
Yeah, it looks like spherical coordinates.
Yeah, it looks like spherical coordinates, except that not quite because of this. But
Okay.
these are exactly the coordinates we used for the Poincare sphere. So if I draw a sphere and attach some coordinate axes, so x, y, z, then basically what I'm saying is that for some point on that sphere, we can come out a distance S1 prime, come over a distance S2 prime and y, and then go up a distance S3 prime, and that locates the point on the sphere. And remember, we said that the Poincare sphere represents polarization states, right? So every point on the surface of the sphere represents a unique polarization state. But notice we did that when we were talking about monochromatic plane wave light, namely fully polarized light. Right? So the surface of the sphere represents fully polarized light. See where we're going with this? Yeah. Okay, well, we'll come back to it in just a moment. First, let's do the following. Let's go over here. Okay. So, let's talk about Stokes vectors for partially polarized light. So we had our measurement I of beta gamma, and if I of beta gamma is equal to 1/2 S0 for all beta and gamma, and S1 is S2 is S3 is 0, then we must have completely unpolarized light. So this would be unpolarized, and our Stokes vector would just be 1, 0, 0, 0. So unpolarized light. Now, notice we could take this unpolarized light and just formally rewrite it. Oh, and I should probably put an I0 out here just to be absolutely correct. I0. I could formally rewrite this as I0 over 2, 1, 1, 0, 0, plus I0 over 2, 1, minus 1, 0, 0. Right? Is that a true statement? What? Okay, well notice if we take this statement and now think back to what it means physically. It says that unpolarized light is a combination of equal amounts of X-polarized light and Y-polarized light. With one caveat. What's the caveat? Is this X polarization state coherent with that Y polarization state?
Not necessarily.
It's absolutely not.
That's not.
It's not coherent. Because we're adding irradiances. The only time you can add irradiances is if you have two incoherent beams.
Oh, so they don't interfere with each other. Okay.
If you have two coherent beams, you have to add the fields, and then you get the interference terms. And we're going to spend a couple weeks on that stuff, and not too long. So when I rewrite unpolarized light as the sum of equal amounts of X and Y polarization, I'm saying that I have equal amounts of X and Y polarization or polarized light that is incoherent with each other. And if I take those and I add them together, I will get unpolarized light. Or on the other hand, if I take unpolarized light and I pass it through a Y polarizer, I will get Y polarized light. Or if I pass it through an X polarizer, I will get X polarized light. But those two polarization states will not be coherent with each other. Okay? So I could also formally rewrite it like this. 1, 0, 0, 1 and 1, 0, 0, minus 1. And what does that say? Yeah, so if unpolarized light can be thought of as a combination of equal amounts of clockwise circularly polarized light and incoherent counterclockwise circularly polarized light. So another way to think about all this is unpolarized light is a linear combination of two equal amounts of incoherent orthogonal states. It doesn't matter which states those are, as long as they're orthogonal. Another way of saying it is, if I have incoherent light, I can create polarized light of any polarization state if I'm willing to throw away half the power. Because all I do is take the unpolarized light, pass it through a polarizer. Now I've got linearly polarized light, whatever angle that polarizer is at, and then pass it through a quarter wave plate, like we learned how to do, at whatever the angle is relative to the polarizer that I need in order to get the polarization state I'm looking for. And then the cost is I'm throwing away half the light. Depending upon what you're doing, that may be worth the cost. So, this is for unpolarized light. What if I have partially polarized light? Well, in that case, the degree of polarization is the square root of S1 squared plus S2 squared plus S3 squared all over S0. And that's going to be less than 1 for partially polarized light. So I could bring this S0 over and multiply here, and then it's the square root of S1 squared plus S2 squared plus S3 squared. I'm just playing around with algebra, really. Which means that if I start off with a Stokes vector, S0, S1, S2, S3, I could rewrite it as 1 minus P times S0, 0, 0, 0, plus P 0, or rather S0, times S1, S2, S3. In other words, I can write this partially polarized light represented by the Stokes vector as a Stokes vector that is completely unpolarized plus a Stokes vector that is completely polarized. So in other words, I can formally separate out the fully polarized and unpolarized aspects of P. Okay. Now, let's go back to this expression right here. And let me rewrite it. Notice I could bring this S0 inside underneath the square root. And if I do that, then I have square root S1 over S0 quantity squared plus S2 over S0 quantity squared plus S3 over S0 quantity squared. And that's equal to the square root of S1 prime squared plus S2 prime squared plus S3 prime squared. Right, where here are the primed versions, they're just the normalized versions. So that opens up something interesting. We're saying that for partially polarized light, this quantity is less than 1. And yet, S1 prime, S2 prime, S3 prime, if I was fully polarized, represents a point on the surface of the Poincare sphere. So if the magnitude here is less than 1, it's a point inside the Poincare sphere. So in other words, all points inside the surface represent partial polarization states. And how much polarization is there? Well, just separate it out like this. This will tell you what the polarized amount is. This tells you what the unpolarized amount is. So if I had this polarization state, say, but it was partially polarized, then if I look at the radial dimension here, I basically go in to, whatever P is, and that's my polarization state. And it's on the interior of the Poincare sphere, therefore I know it's partial polarization. So what does that make the origin of the Poincare sphere? Completely unpolarized. So this brings up another interesting point. What if I had a polarization state over here, and let's say it was fully polarized, I'm on the surface of the sphere. And let's say I added to it light, an equal amount of light, that had a polarization state represented on the opposite side of the sphere. I had equal amounts of those, and I add them together. What would I get? Completely unpolarized light, as long as they're incoherent. So if you want to make incoherent light, and all you're starting with is coherent light, what do? How much? So you're starting off with polarized light, and it's just coherent light. Let's say it's from a laser, but you want unpolarized light.
So we add the same amount in opposite direction.
So take that original state, split it in two, make the other half orthogonal polarization, but they're still coherent. So take this one, let it propagate a distance that's long compared to the coherence length, bring them back together. This tells me the result will be unpolarized. Is that true? Oh, is that true? Let's fire up that projector again. What's this magic touch? Yeah.
Man, the thing is bad.
It's kind of like frosted up, so it's like sagging.
Okay, it's thinking.
Nice.
Okay, so let's go back to this paper that I showed you. It's a really good paper. Okay, so this is 2006, 12 years ago.
Wow.
Which means we did the work 13 years ago. Okay, so we made a few comments about how this is a gyroscope. So it's measuring angular rotation rates. And we'll talk about how using a Sagnac interferometer later in the semester. But we wanted to replace the polarization maintaining fiber coil with something much cheaper, single mode fiber coil. And to do that, you really need depolarizers on the input and the output of the fiber coil. You have to depolarize the light. There's no other way around it. Superluminescent diode is polarized. And these waveguides here just enhance that polarization. So what did we do? Well, we started off with the polarized light, and then we split it. So here, this is supposed to indicate we've got 45-degree linear polarization, and then we go through a polarizing beam splitter. So out of the plane, comes around like this, in the plane, stays like that, and then we have another polarizing beam splitter. We bring them together, and basically, if this path length minus that path length is much bigger than a coherence length, then when they come back together, they're going to be incoherent. And we'll get depolarized light. And this gets back to, where is it? There we go. Where we measure the power as a function of wavelength. So we measure the spectrum. And then we Fourier transformed it to get the coherence as a function of the delay time. And this is why we chose this spot right here, where we had the minimum coherence given that spectrum, so that we have the maximum depolarization in our depolarizer. The maximum amount of incoherence of those two shifted orthogonal states. So that when we brought them back together, we have the maximum depolarization. So it's exactly using the idea that we just talked about. So, Poincare sphere, initial polarization state SA, orthogonal polarization state SB, delay so much in time that they're incoherent, add them together, unpolarized light. So exactly making use of what we're talking about today. So, it's useful stuff. There's all kinds of games you can play if you understand coherence, polarization. Coherence means spectrum for temporal coherence, and then angular size, we're talking spatial coherence, and then polarization state. There's so much cool stuff that you can do if you understand these things. And now you understand it.
So on that previous graph where you showed us the minimum that you chose at a certain time,
Yeah.
what do you mean like you chose that?
So in other words, we made the time it took to go around this path compared to the time it took to go to this path, the difference between the two, to be that 1.44 picoseconds. Yeah. So that we were sitting right in that null.
Excuse me, when you're saying bigger, you mean how much bigger? Like 10 times?
Well, in this particular case, we chose a very specific delay or difference in propagation times. So we'd sit at that minimum as opposed to being over here, say. And the reason why we chose that, just that gives us the maximum depolarization for a reasonably small delay time. And I forget what it worked out to be. It's like a few hundred micron difference in waveguide length, something like that. Yeah. But of course, to do this, then we needed to have polarizing beam splitters in a waveguide device. So, how do you do that? You can't just plunk a beam splitting cube in there. So we designed some some etched high aspect ratio trenches, just the right spacing, just the right fill factor. Turns out we had to tune the angle just right too, so that we could get the TM light reflected and the TE light to go through with a very high differentiation between the two states. And if you know what's going on, you can play the game.
do you take the picture? Or is that the actual?
Oh, this is simulation results. So we wrote our own 2-dimensional and then 3-dimensional finite difference time domain codes to do this sort of design. And we also created a microgenetic optimization algorithm that we piled on top of our FDTD codes to do automatic optimization of our atomic structures. And that was the bottleneck too. Okay, so any questions?
And what was the, I guess, what was the application of like getting the unpolarized light? Like, why did you?
So that gets into how the gyroscope works when you're not maintaining polarization in the fibers, and that's kind of a long story.
Okay.
Yeah, I can tell you a lot of things. Turns out this is some work we were doing for the FAA because they wanted to save several $100 million a year by shutting down the radio navigation system in the United States. There are these radio transmitters all over the U.S., different frequencies, and when you're flying a plane, especially for private pilots, that's how you navigate, especially prior to GPS, is you just figured out what direction the different transmitters were at, and you could triangulate your position. And so that's how you navigated. And then GPS came along, it obviated the need for all of that. They wanted to save money, shut everything down. But then the problem was, what happens if GPS goes out? And you have all these small planes up in the air, and then you can't track their position. You know, what do you do? And so the FAA was looking at mandating that every plane have what they hoped would be an inexpensive inertial navigation unit. And so this was a part of developing such a unit.
Was this before like other types of accelerometers existed, or are they just not adequate for this situation?
They're not really adequate
Okay.
because of the amount of drift you get.
Okay, yeah.
So you need something.
So
really
this is
accurate.
really accurate.
Yeah.
Okay.
But even so, the spec was something like be able to, planes had to get on the ground within 15 minutes. So your navigation track had to be good for at least 15 minutes.
Okay.
But even that requires an incredible amount of precision.
Yeah.
Okay, now at this point, if we had time, which we don't, we could look at how do you use Stokes vectors with a system analysis. And when we were doing Jones vectors, we had Jones matrices to model the effects of various components in a system. So with Stokes vectors, you have something called Mueller matrices, which are 4x4 matrix things that represent the effect on polarization state of various optical components. But in this class, we don't have time to dive into that stuff. But I just mention it so that you're aware there is such a thing.
Are they formed the same way by just doing a big matrix multiplication chain?
Same thing. That's right. Just have a lot more elements. And the hilarious thing, I think, is that a bunch of those elements, no one really understands what they mean, which is just crazy. And I should mention these Stokes vectors, is it a true vector? Turns out it's not. Because, in a vector, you have a basis set of orthogonal directions that you decompose whatever it is you're trying to decompose. Well, in a Stokes vector, these four elements are not orthogonal. So these are not true vectors. Instead, this is just a fancy way of simplifying the bookkeeping, which is linear algebra is usually just that fancy way of keeping track of the bookkeeping. But here we're keeping track of the bookkeeping of non-orthogonal things. So there's duplicate information in these four parameters. And so it's just pretty funny that this is not rigorous mathematics. And therefore, when you go to the Mueller matrices with the 16 elements for each matrix, it's no surprise that people really don't understand what some of the elements represent. So, yeah, so anyway. Okay, well, we're out of time, so Next time what we're gonna do is shift gears and start on reflection